After a black hole reaches equilibrium, when the temperature stabilizes, the Hawking radiation becomes steady and the entropy stops growing. Physicists thought nothing was changing anymore. The black hole just sits there slowly evaporating. But I realized something in 2016 that changed everything. Even after equilibrium, something inside the black hole keeps evolving. It keeps getting more complicated, more scrambled, more impossible to decode. The black hole becomes the fastest computer in the universe, and it never stops computing. Let me tell you how I figured that out. It was around 2014, and I'd been thinking about black holes for decades at this point. The information paradox, my 28-year war with Stephen Hawking, had finally been resolved. We all agreed information isn't destroyed. But there was still this nagging puzzle that kept me up at night. I was in my Stanford office looking at calculations about old black holes that had been sitting around for a long time, radiating steadily. The entropy had plateaued. The temperature was constant. According to thermodynamics, the system was in equilibrium, done, nothing left to evolve. But that couldn't be right. Time was still passing inside the black hole. The quantum state was still evolving according to Schrödinger's equation. Something had to be changing. But what? I remember walking down the hallway to Adam Brown's office. Adam was a brilliant postdoc in my group at the time. I said, "Adam, what the hell is still evolving inside an old black hole?" We started working on this together, along with Dan Roberts and Brian Swingle, and what we found blew my mind. The answer was complexity, not entropy, not energy. Complexity, the computational complexity of the quantum state. Even after the black hole reaches thermal equilibrium, the quantum state inside keeps getting more and more scrambled, more tangled. Harder to describe, harder to decode. The complexity keeps growing for an exponentially long time. And here's what really got me excited, that we conjectured that this quantum complexity is connected to the classical action of space-time inside the black hole. We called it complexity equals action. And it opened up a completely new way of thinking about what black holes actually do. Let me back up and explain the puzzle more carefully. When a black hole forms, say, from a collapsing star, it starts out far from equilibrium. It's violent, chaotic. The geometry inside is changing rapidly. Information is getting scrambled like crazy. The entropy is increasing. But eventually, the black hole settles down. The Hawking radiation becomes steady. The temperature stabilizes. The entropy reaches a maximum value, the Bekenstein-Hawking entropy, which is proportional to the area of the event horizon. At this point, the black hole is in thermal equilibrium with the Hawking radiation bath. Now, in classical thermodynamics, when a system reaches equilibrium, it's done. Nothing macroscopic changes anymore. The entropy is maximal, the temperature is uniform, and time evolution just consists of random thermal fluctuations that don't go anywhere. But black holes are quantum systems. And in quantum mechanics, even a system in thermal equilibrium keeps evolving. The wave function never stops changing. It rotates through Hilbert space according to Schrödinger's equation. So the question is, what's changing inside an old black hole? What physical quantity keeps evolving long after entropy has maxed out? This question had been bothering people for years. Patrick Hayden and John Preskill proved this theorem back in 2007. They showed that to decode the information in Hawking radiation, you'd need to wait until more than half the black hole had evaporated, and you'd need to perform an exponentially complex quantum computation on the radiation. The complexity of that computation is insane. It grows exponentially with the black hole's entropy. That got me thinking. If it takes exponentially long to decode the information, maybe something is growing exponentially i.e. the black hole. But what? Here's the key insight. Think about what happens when you try to prepare a specific quantum state. Let's say you want to build some complicated quantum state from scratch, like the exact quantum state describing all the particles that fell into a black hole over billions of years. You'd need to perform a sequence of quantum gates, unitary operations that manipulate qubits. The more complicated the state, the more gates you need. The minimum number of gates needed to prepare a state is called its computational complexity. For a black hole in equilibrium, the entropy is fixed, but the complexity of the quantum state keeps growing. The state keeps getting more tangled, more scrambled, harder to prepare from scratch. And this growth doesn't stop when entropy maxes out. It keeps going. For how long? We calculated it grows for a time proportional to the exponential of the entropy. For a solar mass black hole, That's something like 1076 times the current age of the universe. That's insane. Long after the black hole looks boring from the outside, long after it's in perfect thermal equilibrium, the quantum state inside is still evolving, still getting more complex. I realize this is the answer to what's still changing. Complexity is the clock inside at an old black hole. So Adam, Dan, Brian, and I started working on a concrete conjecture. We wanted to connect this quantum complexity to something geometric, something you could calculate in general relativity. The idea came from ADAS CFT, the holographic duality that Juan Maldacena discovered in 1997. In ADAS CFT, you have a gravitational theory in anti-de Sitter space, and it's exactly equivalent to a quantum field theory living on the boundary. Anything that happens in the bulk, inside the ADAS space, can be translated into something happening in the boundary theory. So we asked, if complexity is growing in the boundary quantum state, what's the corresponding geometric quantity in the bulk? We propose that the answer is the classical action of a specific spacetime region called the Wheeler-DeWitt patch. Let me explain what that means. In general relativity, you can define different spacetime regions depending on what you're trying to calculate. The Wheeler-DeWitt patch is the region enclosed by light sheets emanating from a spatial slice on the boundary. It's basically the biggest causal diamond you can fit inside the black hole geometry. Now, in classical mechanics, every trajectory has an action, a number you calculate by integrating the Lagrangian along the path. In general relativity, every spacetime geometry has an action too. You integrate the Einstein-Hilbert Lagrangian over the spacetime region. Our conjecture was the quantum complexity of the boundary state is proportional to the classical action of the Wheeler-DeWitt patch in the bulk. Complexity action, why would this be true? Well, think about it. When you perform a quantum gate on a qubit, you're applying a unitary operator. That unitary is generated by a Hamiltonian. The Hamiltonian tells you how the system evolves in time. And the time integral of the Hamiltonian is the action. So quantum gates are secretly related to classical actions. When you build up a complex quantum state by applying many gates, you're effectively exploring a huge space of possible time evolutions. The complexity measures how deep into that space you've gone. And the action measures the same thing from the gravitational side. This was a beautiful connection. Quantum information theory, the study of circuits and gates and computational complexity, was linking up with general relativity and black hole geometry. And here's the punchline: when you calculate the action of the Wheeler-DeWitt patch for an old black hole, you find that it K-E-P-S-G-R-O and Ga. Long after the entropy has maxed out, the action grows linearly in time. For how long? For an exponentially long time, proportional to XPS, where S is the entropy. This matched exactly what we expected for complexity. The black hole's quantum state keeps getting more complex, and the bulk geometry reflects that growth through the increasing action. Now, I have to be honest with you. This was a conjecture, not a proof. We couldn't derive it from first principles. But we checked it in lots of different examples, different black hole geometries, different boundary states. And it kept working. The relationship held up. Since then, hundreds of physicists have worked on this program, refining the conjecture, testing it in new contexts, exploring its implications. My student Adam went on to do incredible work on this with other collaborators. The complexity action program has become a major research area in quantum gravity. But here's what I find most profound about this idea. It tells us that black holes are not just black holes. They're computers, quantum computers, and they're the fastest computers nature allows. When we first put this conjecture out in 2016, the reaction from the physics community was mixed excitement and skepticism. That's pretty normal for big new ideas. Some people immediately got excited. Juan Maldacena, who's probably the smartest person I know, thought it was a really interesting direction. He and other ADAS CFT experts started exploring what complexity could teach us about black hole interiors. Ed Witten, who's sharper than all of us, raised some technical questions about how to properly define complexity in quantum field theory, and he was right to push on that. Complexity is easy to define for systems with finitely many qubits, but for a quantum field theory with infinitely many degrees of freedom. That's subtle. We needed to think more carefully about what we meant. Other researchers pointed out that there are actually multiple ways to define computational complexity. You can count gates in different ways. You can use different gate sets. You can consider different notions of distance in the space of quantum states. So which complexity corresponds to the action? We had to figure that out. And then there were the holography skeptics, people who don't buy ADS-CFT to begin with. They said, look, you're making a conjecture about a duality that's itself conjectural. How can you test this? Fair point. But here's the thing, ADS-CFT has passed thousands of tests over 25 years. It's as solid as conjectures get. And our complexity conjecture made specific, testable predictions within that framework. Over the next few years, my group and others worked on sharpening the idea. We explored different black hole geometries, rotating black holes, charged black holes in different dimensions. We looked at what happens when the black hole is far from equilibrium or when it's perturbed by shock waves. We studied the complexity geometry of the space of quantum states. Adam Brown and I wrote follow-up papers exploring the details. We worked with Ying Zhao on connections to momentum and energy. We collaborated with Dan Roberts and Brian Swingle on relating this to scrambling, how fast information spreads through a quantum system. One of the coolest results came from a paper we called The Python's Lunch. Adam, with collaborators Alex Garabian and Geoff Pennington, showed that there are geometric obstructions in the black hole interior that make it exponentially hard to decode Hawking radiation. The geometry itself, the curvature of spacetime, creates a computational barrier. We called it the Python's Lunch because the information is trapped inside a long, winding region of spacetime, like a mouse inside a python that's slowly digesting it. This connected directly to complexity action. The harder it is to decode the information, the more complex the quantum state. And the more complex the state, the larger the action of the interior geometry. It all fit together. Then in 2022, something incredible happened. Adam and others showed that you could simulate wormhole-like dynamics in a quantum computer, and they actually did it working with Google's quantum computing team. It was published in Nature. They weren't simulating a real black hole, of course, but they were testing the kind of quantum circuit complexity that we'd been talking about. And it worked. That's what I love about physics. You start with a crazy abstract idea, maybe complexity equals action in a black hole, and a few years later, people are testing related ideas in actual quantum computers. Not everyone is convinced yet. Some researchers still prefer other approaches to understanding black hole interiors. But the Complexity Action Program has become a major player. There are conferences about it. Graduate students write theses on it. It's part of the landscape now. So where does this leave us? What are we still trying to figure out? Well, one big question is, does complexity always grow? We conjectured that it does, that there's a second law of quantum complexity, analogous to the second law of thermodynamics. Entropy always increases in a closed system. Does complexity always increase too? Adam Brown and I wrote a paper arguing yes. At least for black holes and systems in ADS-CFT, complexity seems to grow monotonically until it saturates at some maximum value. That maximum is exponentially large in the entropy. It's the size of Hilbert space, basically. And the time to reach that maximum is exponentially long. But proving this rigorously, that's hard. We can check it in specific examples, but a general proof is still out of reach. Another big question, what does complexity teach us about cosmology? We've been focused on black holes, but what about the universe as a whole? Our universe is expanding, accelerating, heading toward a de Sitter-like future. Does complexity play a role there? That's something I've been thinking about a lot in recent years. De Sitter space with a positive cosmological constant, is why harder to understand holographically than ADS space. I've been working with Edgar Chagolian and others on de Sitter holography, and one thing we're exploring is whether complexity can help us understand the structure of the cosmological horizon. There's also a deep connection to quantum computing itself. If black holes are the fastest scramblers in nature, and I conjectured that back in 2008 with my student Yasuhiro Sekino, then they're also the fastest quantum computers. Understanding their computational limits might teach us fundamental limits on any quantum computation. And then there's the firewall problem. Remember the AMPS paper from 2012 that claimed black hole horizons must be firewalls, walls of infinite energy? I responded with EREPR, but complexity offers another angle. Adam and I, along with others, showed that creating a firewall requires an exponentially complex quantum operation. For black holes formed from gravitational collapse, that operation is essentially impossible to perform in finite time. So firewalls probably don't exist for realistic black holes. But for old black holes that have been sitting around for exponentially long times, maybe firewalls eventually form because the complexity has had time to build up to the point where the geometry can be manipulated. That's still an open question. After all these years, black holes keep surprising me. Every time I think we've figured them out, they reveal another layer. First it was Hawking radiation, then information paradox, then complementarity and holography, then scrambling, then complexity. I'm 86 years old now. I don't know if I'll live to see all these questions answered. But I know this, the next generation of physicists, the students working on this right now, they're going to make progress. They're going to push it further. And that's what physics is about. Let me leave you with this thought. For a long time, we thought of black holes as the ultimate destroyers. Things fall in, information is lost, or so Hawking claimed. But over the past 50 years, we've realized black holes are actually the ultimate information processors. They scramble information faster than anything else in nature. They store information more efficiently than anything else, 1 bit per Planck area. And they evolve quantum states through exponentially complex sequences of operations. Black holes are nature's quantum computers pushed to the absolute physical limit. And what are they computing? We don't fully know. Maybe they're computing their own quantum state, exploring the vast landscape of possible configurations in Hilbert space. Maybe they're computing the answer to the information paradox, how to encode all the information that fell in onto the outgoing Hawking radiation. Maybe they're computing something we haven't even thought of yet. But one thing is clear, they never stop. Even when entropy maxes out and the black hole looks completely static from the outside, the interior keeps evolving. Complexity keeps growing. The computation continues. It's like the universe itself is constantly calculating something, and we're just beginning to understand that's the beauty of physics. After 50 years of studying black holes, they're still the most fascinating objects I know. And there's still so much left to discover.